Hello everybody, Sean from SMD Methods here, and you are all very welcome into this third of what should be a three-parter on using a Runge Kutta 4 solver for a solution to a second order ordinary differential equation, modeling a spring mass damper system. So in the first two videos we took a kind of a written based workflow to solve the first time step, which was from t is equal to 0 to t is equal to 0 plus h being the time step, selecting the time step of 0.2 seconds. So in the last video, in video 2, we established new velocity and position values, which gave us updated velocities and positions from the initial values, i.e. the values that we had at t is equal to 0 for velocity and position. Now, them initial values, as well as a full description of the problem, were taken from problem 25.16 of Numerical Methods for Engineers, edition 8 by Stephen Chapra and Raymond Canale. So in this video, I'm going to move into MATLAB, and what we'll do is we'll set up a loop so that we can solve for each and every time step in that 0 to 15 second time interval, again using the time step of 0.2. And we'll be able to validate our velocity and position values at the 0.2 time step from MATLAB. So what we'll do is we'll store our values as we go along. So I'm going to come on in here to MATLAB. So this is just legacy from our last video. I'm going to start in a new script. I'm going to move into text here, maybe choose heading 2, and what I'm going to do is maybe call this spring mass damper. Don't know, incidentally, why it's spring mass damper as opposed to mass spring damper or damper mass spring or damper spring mass. Spring mass damper is what I've always known it as. Maybe if a viewer knows why the words are put in that order, please let me know. But I like to think I see SMD in it, just like SMD methods. SMD is my name. Incidentally, it's not because of spring mass damper. So spring mass damper solved by RK4. Maybe move this down to heading 3. This is problem 25.16, Numerical Methods for Engineers, edition 8. Okay. So let's put in a section break in here. Let's write our parameters in the first section. Makes as much sense as anything. Parameters, let's come back into code. M is equal to 20. Just give myself enough space. This is mass. I won't bother writing in kg. I'll just put kg in brackets. C, our damping coefficient, we used 40. Problem asks us to use 5, 40, and 200, which is under critically and overdamped scenarios. In our written base workflow, we used 40. So we'll start with 40 and we can check the others. This is damping coefficient, and that of course is Newton seconds per meter as a unit. K is equal to 20. This is our spring constant. What I'm actually going to do is call this Ks for spring constant, because indeed we have Ks, which are the slope values for the f function, and just to avoid any sort of confusion, let's call this here the spring constant. And that, of course, is newtons per meter. What are the parameters? That's all kind of the system parameters: the mass, the damping, and the spring constant. So yeah, I'm going to leave that there. Let's put in a section break, new section. I'm going to go to text, and let's put in, let's see, let's call this computational provisions, references. Don't know what you can call that, computational provisions. This is what we need for RK4. Come back into code. First thing I'm going to set up is a step size, 0.2. This is going to be our step size. That's in seconds. We want to set up a vector, our time interval, what we're solving for, the time periods that we're solving for. So let's give a space, put this out separate. T, it's called T. We're told to go from 0 till 15 seconds, and we're using a step size of h, which is 0.2, 15. So this is going to be our time interval for the solution. Time interval, these are measured in seconds. For every time period, for every time reading, I'm going to have a velocity, and I'm also going to have a position. So I'll set them up now. I'll go for a velocity. V is going to be equal to zeros, just to initialize the variable. I'm going to go for one row, and then how many columns I need? Well, I need one velocity value for every time value. So I'm going to write these out in the columns. So every time value is going to have a new column. So I need a velocity value that has columns, or a velocity vector that has columns that is equivalent to the number of elements in t. So let's call this one here our velocity value repository store. These are all in meter per second. And of course x, we're also going to have positions at each time step. So I'm going to say x is equal to v, just for equivalent, because it's going to be the same size. It's going to look the same. This is going to be my position value store. Positions are measured in meters. All right. Now, I think what the next part is, what we'll do is we'll initialize. We'll put in our initial value. So we'll need a starting value, t is equal to 0 for v, and a starting value at t is equal to 0 for x. And those are given to us in the question, and we've gone through these a couple of times in our solution, our written solution. We're given it to here. Initial velocity is 0, so v1 is equal to 0, and initial displacement is 1, so x1 is equal to 1. We don't have to do anything with v because they're all zeros at the minute, including the first 0, but just so that we have the space to alter a starting velocity value, let's set up a definition here for it. v1 I'm going to set up as to 0, and that there is my initial velocity value, of course in meters per second, and x1, the first value in the x vector, is equal to 1 meter. That there is the initial position value, meters. Okay, now there's the competition provisions, the spaces that I need. What I'll do is I'm going to put in a section break. I can put into this, really this next part, but maybe it'll make a little bit more, not more sense, but just for an organization perspective, just to completely separate these different bits. I'm going to put in this section here, maybe RK4, we'll put in here RK4 slope stores, or RK4 solver facilities. Struggling for nouns here, descriptions. Let's stick in a little bit of code here. So what I want is, I want a place to solve or to store all my my k's, all my slopes for the two functions. Right. So let's go for a k store, and these are going to be all the slopes there for my f function. There's 4 of them, k1, k2, k3, and k4. So what I'm going to do is make this as zeros. I'm going to put in 4 rows. Each row is going to have its own k. So row 1 is k1, row 2, k2, row 3, k3, row 4, k4. So 4 rows for 4 k values. And every time step or every iteration, numel of t, is going to have a k. So I'm just going to set it up that we have our 4 rows, and what's going to be effectively 75 t's, 75 columns, if you like, 75 t values there, which is 15 seconds, and then them seconds are split into fifths. And of course L, which are my slopes for my g function, so that there's going to be equal to k at the minute size wise. So let's define what this is. This is going to be my k slope store, that there is for a function. And oops, let's go down. And then of course this is my L slope store. That there is for the G function. Okay, let's put in a section break here. So I'm getting a wee bit crazy with section breaks and whatnot, but why not? You can incidentally, run these sections individually. There's probably little reason why I'd want to run these individually just for this particular example, but I do, maybe as you can gather, enjoy breaking the code into specific sections. Maybe more so than for organizational purposes than for, modular calculation or computational provisions. In this one here, we'll define our functions. Let's see, function definition. Of course, you can always just percentage sign and comment before you write what you do, as opposed to putting in new sections and texts. The function definition, we have two functions. We're going to do these up as a handle, which is probably be as handy. F is going to be equal to at open bracket, and my inputs for the f function. So don't forget the f was the dx dt. It's going up to where we had it here. Here we are here. F function was dx dt, and there's only one input, it's just the v in it. So I'm going to put it in here. I'm just going to put in the v, and I'm going to call it v underscore in, like the v input, as opposed to just v, because v is a full row vector here. V in, and the function itself is indeed v in. That's where v in goes. It just goes there. You just put the v in value in. I'm not going to bother writing t in and x in. Don't need it. All right. The g, that's the minus 1 over m multiplied by the c by v plus k by x quantity function. So that has a v in, and it also has an x in variable to use, and that function there is given by minus 1 divided by m multiplied by our c value, which is given all the way up here, c value 40. Let's see if I can pull that down a wee bit, give myself a wee bit more screen real estate. C multiplied by the value that I'm going to put in here, I'm going to call it v in, right, plus open bracket ks, spring constant there, multiplied by my x in value, x in. Now what I'm going to do is I'm going to obviously put another set of brackets there to make sure that the minus 1 over m is applied to that entire quantity as opposed to just the c by v in quantity. Semicolon that. So this is just as a comment. This is my f function, which is indeed dx dt, solves for x, and this is my g function, g of t. This one solves for dv, is dv dt, which solves for v. That's it. Let's put in a section break code with the text, and let's put in RK4 computations. K's, L's, and indeed V's and X's. Code. So for this one, I'm going to put in a for loop, and I say for I is equal to 1 up till the number of elements in T. Now, there's two ways of setting this up. I can say that I'm currently at I minus 1. So in that case, I would have to set that up to start at 2, because I minus 1 is 0 for these indexing. These indexers, you have to start at 1, there's no 0. Or else I start at I is equal to, the current is equal to I, and I search for I plus 1. If I search for I plus 1, by the time I get out to number element t and I'm running the calculations there, it's going to be looking to solve for me a number of t, that number plus 1, which is going to put me outside the bounds of the array. So to keep myself in the bounds array, I'm going to subtract 1 off of the last limit. So what that means is that when I'm at num_L of t, which is going to be 75 minus 1, so when I'm at 74, it's calculating me an I+1 value, which will be the 75th value, which is at the 15-second interval. Okay, if that is not clear with anyone, please drop me a message and I'll be more than happy to show it in MATLAB how that works. But just to keep things moving on along here, you can take my word for it. So what we want to do is we want to set up our k value, k1 solution, L1 solution, k2 solution, L2, k3, and so on. So k, my first row is k1 of my ith column for my current iteration. Right? So the k values use the f function here. So the f function, what we're going to be using is just vin. So we know there that the k1 value is just the function value itself. So what I'm going to write here is that my function value for my first iteration is simply v of I. Right? That's my input, v of I. So v in here is v of I. Sorry, I have to put in the function value, so I'm going to be using, apologies, I did say it and I didn't put it in. It's the f function I want to run with, and I'm putting in v of I as my input. So v of I is my first, well in this case it's going to be 1, which will be my first v value, which incidentally is 0. Right, I'm just going to be sticking that into there. Right, now for L, this is slightly different because this has a longer function, Li. Right, so L uses the g function. But what I need to do is indeed I need to put in both v of I, all right, and I also need to put in x of I. Right, so, and it's going to execute this function here. Putting v in, v of I there, which is my first variable, and x in, which is my second variable, which is x of I, into there. There. Okay, that's it. Now, k, for my second k value in my first iteration, I'm again using my f value, of course. Now, this one, remember, takes the adjustment. So if I had my independent variable, which would be t, I would be doing t plus 1/2 of h, but I'm going to ignore t because it doesn't appear in the f function. The v value, right, is the solution to the dv dt. The dv dt, and this is my g function. The g function is has attributed to it the L slopes. So I'm going to take my current v value plus 1/2 of h multiplied by my L, my most recent L slope, which in this case is L1. So I'm going to be running the f function, and my v in value for this is v of I, right, v of I plus 0.5 1/2 of h, right, times our k, our most recent k value, but it's k1 of I. So this is the adjustment that I make to my v. I go over half a step, 1/2 a step by a, yes, 1/2 of the step size by the slope gives me my new adjustment to the v height. Add that onto my current height, and I'm into my new value, my new v value, my adjusted v value, which is given here. You can see it there, v plus 1/2 of the step size multiplied by L1, which is v plus 1/2 of the step, multiplied by L1, apologies. And I was after saying that at the start. V is going to be the solution to dv dt, which is the g function. The g functions use the L slopes, L slope. Now, the L slope for 2I is going to be equal to the g function. I'm going to be using the same identical v of I function here. Control C. So I'm opening up my bracket, but I'm going to put this in its own little bracket because this is the first entry. And then comma, I'm going to put in the x one. So we do x of I plus 0.5 times h times the k slope. And the most recent k slope is k1 of I. So I'm going to put this into its own bracket as well. And this is my overall bracket. So it seems to be a lot of brackets, but this outside one to there just is the bracket to prompt to put in the inputs. My first input is running from that open bracket to there. There's my first input. I just bracketed it all off. And my second one is also all bracketed off there. That's it. Now, I'm going to copy these for speed because K3 and K4 have the same adjustments, except we just need to update what's the most current slope. So by the time we're at K3 and we're at L3, right, our most recent slopes are no longer L1 and K1, they become L2, L2 and K2. They're the most recent slopes. And then when I get down to K4 and L4, I do V of I plus not a half of H, but it's a full step size plus one full H of my third is the most recent slope. So again, take away the multiplied by half of a H because we're doing a full H. The third L value is third slope for here. And again, I'm taking out the 1/2 of H here multiplied by K. This is going to be the third K. So that should work us out all our K values and our L values in this loop. Now, when I get to the bottom of the loop, I want to calculate out my new velocity and indeed my new position. So I'm going to be populating V of I plus 1, which is my next V value. So this is going to be the Runge Kutta formula itself, which is given here. I'm going to do the V of I first. So the V of I is equal, I plus 1 is equal to V of I, my current one, plus this adjustment. So bearing in mind that V is the solution to the dv dt function, which is the g function to which L's are the slopes in. So V of I plus 1 is equal to V of I, my current value, plus 1 divided by 6 multiplied by, take the multiply out, inside the bracket, multiplied by all of this stuff, which is going to be my L of I, my current value, plus 2 times, apologies, 2 times L1 of I, L1, plus 2 times L2 of I, plus 2 times L3 of I, L3 by I, plus L4 at I. Close all them brackets. Right, so I'm going to sum all them, multiply by 1 by 6, and then indeed multiply that there by my step size H. And that should work me out what my new V value is going to be. And indeed, X is going to be the same. Undo that, Control Z, Control C. X is going to be the same, except where X, I'm going to use this X value, and I'm not using, X is the solution to dx dt, which is the f function to which k's are the slopes for. K, 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 K. Okay. So yeah, that should do it. So let's try a run here and let's see how we go. Everything has seemed to work out okay. There's been no errors. We can check our values in through here. But what I'll do first is I'm going to maybe just put in a section break, text, and let's just do a very quick plot of the two of these code. Let's run plot t against v, and we'll also plot t against x. Yes, I completely know that I have not put in titles or grids or x-axes or legends, and I just want to get an idea of what these look like. So this is critically damped, so what I would expect to see with velocity is a dip down below and then a come back up and then to even off. So we might get like one like what will look like a minima and then come up from zero. Yeah, it'll look like a minima because if we go in the negative direction, it'll come up and stop. Whereas the what I hope to see with the position is it starts from 1 and it comes straight, it just smooths off at 0. That'll be critically damped. So let's see what it looks like. Running it again, and there we are. So that looks good. So if we look here, this is our first one, which is the velocity. So just as I said, it looks like we hit a minima. Comes up and it damps off, which that looks like proper behavior for the velocity profile of a critically damped system, as does that. Right, we don't have any oscillatory behavior in that. Now what I would also like to do at this stage is I'm going to open up my my K matrix and see what these values are. So this is K1, K2, K3 and K4, which is 0, minus 0.1, minus 0.08 and minus 0.166. I'm going to compare that to our handwritten exercises. K1 was 0, minus 0.1, minus 0.08 and 0.166, which we have agreement with them. So that would indicate that our written workflow was done correctly. L, minus 1, minus 0.8, minus 0.83 and minus 0.652. So looking at our L, minus 1, I can't remember what these were, minus 1, minus 0.8, minus 0.83, minus 1, minus 0.8, minus 0.83, and minus 0.652, minus 0.652. So again, we have agreement with our L slopes, so K and L both look good. Let's now check our velocity. Our velocity was 0, was our initial velocity, and then after time step 1, which is after 0.2 seconds, we were moving to the left at a speed of 0.1637 meters per second, so our velocity is minus 0.637. And coming into here, velocity minus 0.1637, so our velocity is right, and hopefully then our x position should be right at minus 0.9825 at t is equal to 0.2 minus 0.9825. Yeah, so our written, I can validate that our written solution, our written workflow has been verified by the calculations that we calculated out here using MATLAB. So the arithmetic was right. Hopefully the modeling has been right and there's been no mistakes, but I don't think that there is. It looks pretty good. Where you might get mistakes, it's very hard to know. You know, you miss a decimal point, you could still get this sort of shape, and it might not necessarily be, you know, an accurate physical representation of the response of the system. Maybe it is, but however, the question here has asked us to check this out for 3 values: underdamped, critically damped, and overdamped. So we've done critically damped. Let's have a look at what underdamped looks like at 5. So if I change 40 and let's move that to 5 and let's rerun again. Yeah. So here what we see is our velocity again, takes the initial bump, with speed we overshoot, and we're oscillating. But our velocity is steadily decreasing, which would be expected. And we can also see here as well that our position is oscillatory as well, but as we oscillate, the damper is successfully draining energy out of the system, albeit at a very reduced rate at 5 Newton seconds per meter relative to the 40 that we're at. And you could see there we're kind of all shifted by roughly the 90 degrees of that. So the optimism that is kind of at the points of inflection above in all these cases, which indicates pretty much so expected behavior. And then our overdamp case, I believe, was 200, which in this one we could probably all guess what this should look like, which would be a very uncomfortable ride. What we would like to probably see is a very hard stop here. Is what we get here. So our velocity both just hits off, and then we come back very quick. And here what we do is our position has well, it still looks progressive enough. Doesn't look too bad. But you can see the velocity there. It's just an instantaneous shock in, and then letting go, if you like. So again, don't forget the damper there. The damper effect is a function of velocity. So the faster you go, the more damping you get. So you want to compress a damper. It's easier to compress it if you take it nice and handy, or extend it indeed, as opposed to trying to shock it in. The damp works. And so let's just try 40 again, just as a. We could overlay these, of course. We could hold on, and we could check these. So there is that 40 has just dropped from 1, and we are, say, roughly about 7.58. We're down at 0, 7.58 seconds. If we overdamp that, right, there it goes. We haven't even reached because our velocity is so fast, it's still pulling energy out of the system down to 0. Very progressive. So yeah, there's the MATLAB solution done for this. So we are at 32 minutes. This has extended over longer than I thought it was going to do. So what I will do is I just do the SimScape. I'll do the SimScape solution to this in the next video here, just so you can maybe digest some of what has been done here, and also give you a chance to, again, hit the subscribe button. Come back to me with any questions, comments, clarifications, suggestions, whatever you like. If you want a copy of the code, no bother, just ask, I'll give it to you. Yeah, then you'll also get a notification, of course, you are subscribed to, when this next video on the SimScape solution will be ready. Okay, so yeah, thanks very much for staying with me through this video, and I hope you do come back to have a look at the next one. See you then.